So I'm going to be bringing the panelists on stage 1 second, and I hope you are enjoying your time with us here. And yeah, we hope you continue to stay with us on the technology track. And we are about to discuss a topic that is dear and near to my heart, and I believe on the lips of a lot of people. So 1 second as I get our presenters on stage. Hi, ladies. I hope your day is going well. Thank you so much for joining. We're waiting for Humna to join us so we can get started.
I think I'm here.
Thank you all. We will start with a brief introduction and welcome. We have 4 panelists, and the topic of this panel is factors affecting AHEM product quality. As additive manufacturing take the world by storm, as everyone starts to look at additive manufacturing as a technology that can be another tool in the toolkit for manufacturing across different industries, from automotive to aerospace to consumable goods, we are seeing adoption of additive. But the question on the mind of people who are related product is really, what are the qualities that we can get out of these technologies? Which one offer the best quality? Are there some trade-off if you go from one technology to another? Are the quality really shifting? And today I brought you 4 panelists who will be discussing these topics with us and sharing their insights across the board. We have 2 people who will be talking about polymer quality, and 2 other people will be talking about metal related quality, and I'll be chiming in and taking questions. On this panel, we have Andrea Benz, who is the Director of Quality Management at Big Metal Additive. We have Brenda Jones, who is the CEO of Lendo Technologies, Inc. We have Muna Khan, who is the CEO and founder of Astro Mechanical Testing Laboratory, and Laura Kramer, who is a materials and R&D manager at 3D Systems. Welcome, everybody. I'll give you the floor to introduce yourself, starting from Andrea. If you can say a few words about yourself, we're ready.
Thank you, Addie. It's great to be on this panel today. I'm the Director of Quality Management at Big Metal Additive. We use hybrid additive manufacturing to produce metal components for customers in various industries. One of our largest customers is the U.S. government, but we also make products for aerospace, space, energy, and automotive industries as well.
Thank you. Humna, can you go next?
Okay. I'm Muna Khan. I am the Astro Mechanical Testing Laboratory, CEO of Mimo Technique. Mimo Technique Print Metal. We are large format laser powder bed printers, and we're manufacturing on space materials for space flight hardware for every major city and prime. And then Astro Mechanical Testing Laboratory, we do all of the mechanical testing and also metallurgical testing of additive material and additive components. Combined, they kind of work in a close supply chain loop to develop and qualify parts.
Great. Laura?
Okay. I'm Laura Kramer from 3D Systems. I'm a manager on the materials team at 3D Systems, and we cover a whole span of different technologies and materials, including polymers and metals. I have focused on the polymeric materials, and specifically I manage our characterization lab, where we do a lot of the testing, supporting the materials development and also printer development to develop new products. And we also create the data sheets that we use for all of our polymeric products.
Brenda?
Yes, Brenda Jones. I'm the CEO of Lendo Technology. We are a spin-out of the University of Michigan, focused on software innovations to advance 3D printing and industrial robotics. Our first product is a vibration compensation software that, when installed on the controller of the printer, doubles the speed with the same quality.
Thank you. Thank you all for the introduction. We will start with Andrew with the first question. The focus of everybody is on industrializing additive, taking it from where we usually know that it was, which was prototyping, to now a production level. And we're wondering, why is quality vital when you're thinking about industrialization of additive manufacturing?
Absolutely, Addie. I'm happy to answer that question. So as you mentioned, quality is an important topic for additive manufacturing. Generally speaking, additive has started as a novel technology and really opened our eyes to new possibilities. With it, we could make so many new things. We could truly harness the power of manufacturing at the individual level. Make what we wanted to make when we make it. New innovative designs were now possible and lead times were drastically reduced. Additive manufacturing has established itself as an amazing technology, as you mentioned, for rapid prototyping. It gives us design flexibility and the ability to print on demand. But the question that people are now asking is, how do we use additive manufacturing to produce functional products? I think we can all recognize the impact of additive manufacturing being a viable source for manufactured goods. One critical component to this is customer confidence and trust. A customer will buy manufactured goods when they trust the manufacturing process. A major component to customer trust is found in quality. What I mean by quality is the ability to meet customer requirements through a documented and demonstrated set of controlled processes. When a manufacturing process can demonstrate that it can produce products that meet customer requirements, and it can do so reliably, customer confidence and trust is gained. Every time this is achieved, it elevates current customer trust and spurs curiosity and interest in new customers. This cycle of gaining trust through quality will fortify additive manufacturing's position as a viable source for manufactured goods. And really what this allows is for the message from our industry to customers to shift. It'll go from highlighting the benefits around innovation and speed to a message of being a trusted source for production. While traditional manufacturing methods establish quality standards and specifications, it's only relatively recently that additive manufacturing has developed some of its own standards and specifications. What this means is we can now guide our customers through this quality journey using standards specific to additive. And this will bring the industrialization of additive manufacturing and solidify it as a true source for manufactured goods.
Thank you. Thank you so much. So we all know that from one industry to another, the kind of quality you're looking for, they're different. For people who are in consumable goods who are their quality requirements are different. For people who are trying to make prototypes, the quality requirements are different. And if somebody is trying to put a part in a plane, the requirements are all different. Now we're wondering if you can share about this. How does metal AM standardization and quality requirements differ across the industry?
So my background is in space technology. 99% of the parts that I've manufactured are space flight hardware. So they're at a little bit of a more critical level when it comes to industry specifications, and also based on customers, and also launch pad specifications. So we'll take a standard like say and it have to flow down to supplier and process that's involved in the actual. So when it comes to number one, qualifying the material that's going to be used to produce the parts, and the machine that those parts are going to be produced on, and then an entire traceability from when the part is grown to when the part is technically grown. So that can do with metallurgy, it could do with mechanical, and that's just the small part, the witness part of the print. but then the print also has to withstand several other tests, whether that mean vibration or pressure or any test. There is very, very strict standards for all of this, and it's almost a whole plethora of standards from what industry down to what the customer is, and all of those to be met. So I would say say a small component, we probably are complying 20 to 30 different standards, and that may have to do with materials, component, the printers, and anything else that the customer needs to prove in order to be a critical piece of hardware on mission. It differs greatly from automotive or from medical, and even from aerospace, where aerospace has manned, it's a manned vehicle. I talk those are manned vehicles. A little bit more stringency than that, but the costs are so much higher for aerospace parts that there's a bunch of rules to make sure that we don't blow up.
Thank you, Humna, for sharing that. Laura, we know that the quality that is required from a critical component that goes into an engine, even if it's polymer, could be a whole lot. Can you share with us some of the most important factors affecting the quality of AM polymers? And what are some of the sources of variability in polymer AM if you're coming across some of those variabilities?
Thanks, Addie. That's a really good question. Let me answer this using photopolymers and DLP printing as an example. I'm particularly familiar with the Figure 4 printer and materials from 3D Systems, but this should apply to all of that photopolymerization, so other DLP and SLA systems. And I think conceptually, some of the concepts will be extended to other printing technologies as well. So ultimately, we're talking about the quality of the finished object. Does it meet the needs of its intended application? And that might be its physical properties, geometry, tolerances, dimensions, long-term stability, and I'm sure there's lots of other factors that could be considered. So we can think of the material going through several different stages on its way to becoming that final object. First, you manufacture the UV curable resin, and then after some period of storage, you're going to load it into the printer, and the object will be printed. The object's going to come out of the printer covered in resin, so you're going to have to clean it off. And then in most cases, you'll also have a final UV curing step to complete the polymerization. These types of technologies use supports of the same material. So those usually have to be removed, that mechanically or broken off or cut off, and sometimes maybe some final finishing, for example, sanding off the witness marks from those supports. So in terms of quality, we have to think about quality every step of the way through this process. The starting resin has to be manufactured using good process control, and there need to be QC measurements to ensure that there's good batch-to-batch consistency. Then you're going to stick that resin in a bottle, and it's going to have some time for storage and transportation. Typical shelf life for the Figure 4 materials is 2 years. So it needs to be stable while it's waiting to be used, and then it also has to be compatible with the printer system. For example, it can't react with something it's touching in the printer, like some tubing or something like that. Then we get into printing that material, and the printing process has many variables which can affect the quality. A few of them might be light intensity, light uniformity, exposure time, pumping between the layers, and there's many more factors. I'll also mention that the orientation of the printed object can be a factor for some technologies. It usually isn't a big factor for DLP, but you can imagine in some technologies where there's a big difference with being with the layer lines or across the layer lines can make a big difference. So once we've controlled these factors in the printing, we also have to think about differences from printer to printer. So you need to have good control of the printers so that you get reproducible parts, even if you're using multiple printers for your operation to print a lot of parts. So then once you've printed the object, you have to post-process it. So you have to clean it and cure it. And this is a particularly critical time for the DLP materials because they aren't completely cured at this point. So they're more susceptible to damage due to the cleaning or the handling. So it's really important to pick a cleaning solvent that does clean the material, but as gently as possible. And you want to minimize the time in the cleaning step. For our figure 4 materials, we keep the cleaning time to less than 10 minutes. We've also found for best results, the cleaning process needs to be customized for every resin, and one size does not fit all. If you take a look at our user guide for the figure 4 materials, you'll see several different buckets of cleaning protocols depending on the material. Once that material is clean and the object is going to get its final cure, and the process conditions of the cure station also can have a big effect on the final properties. So some of those factors might be light wavelength, the intensity of the light, the temperature that you're doing the curing, and of course, how long you cure for. This is a super important step because for many of the UV curable materials, the properties improve dramatically with this final post-cure as the final linkages are made in the cross-link structure to give you the final properties. So now you've got your finished object and it's meeting all its initial quality requirements. We might also need to consider the long-term stability of that object. So what environmental factors might the object be exposed to during its useful life? So some of the factors we consider are thermal, chemical, UV, and weather exposure. And I can talk about that a little bit more later, but for now, I'll pass it back to Addie for the next question.
Thank you so much, Lara. You know, when we think about polymer, people just think, oh, you print it out, that's it. And we usually just think about FDM. But just hearing from you that with polymer, there are different types of technologies, and there's so much more than just you print it and you use it. Thank you for that detailed explanation. Now, when dealing with the machine itself, there are different issues that could happen that affects the product in the hand. Brenda, I'm wondering if you can share with us some of the issues that your customers and prospects have shared with you that are causing or hampering their quality when it comes to the product they're producing. That would be great.
Yeah, to amplify, Addie, to amplify your introductory comments, I think we probably all know that the adoption of additive really it originated in prototyping and it expanded into low volume and customized parts. But we've also heard that there are challenges in high volume repetitive parts. And some of our end customers say, look, I have to make sure that part number 1 looks exactly the same as part number 10,001 to some extent, right? And often these kinds of parts need to be low cost. So subtracting manufacturing approach has tended to be faster and higher quality. So it's kind of hampered the adoption of additive in this area because the ROI just isn't there vis-a-vis subtractive. The adoption of additive in these, like I say, in these scenarios has been a little slower than we would have liked. So why? Why is that? What are the underlying reasons? Well, there are multiple ones, but what our company is focused on is the thing that's driving speed and quality issues is vibration. And at the risk of being Captain Obvious here, I think we all know that if we try to operate, say, an FDM printer at a high speed, it vibrates, which creates surface blemishes, and at the worst case is layer shifting, just wasted time and wasted materials. We've heard from customers that as high as 20% of their prints fail in the field. So that's not great for efficiency, and it's also not great for the environment because some of those materials just can't be, they potentially can't be reused or recycled. What we've been told that end users do, and I am not an end user of a 3D printer, but I hear that there's a lot of trial and error that happens. And what folks end up doing is they use trial and error to find out the fastest speed at which they can print whatever part they want without getting these quality issues. So that's just not a great solution. It's not a great solution. Or they just buy more printers, which doesn't help a small to medium-sized company. Some people add aftermarket, they add stiffening or dampening parts, but what that does is it adds weight to the printer. That means that it takes more energy, and that's not great for the environment either. And then there are also ultra-fast printers that can print high quality at fast speeds, But often, the small to medium-sized manufacturers are just saying it's just not in the cards for them. It's just too expensive. So we're basically focusing on our company is focusing on trying to compensate for the vibration that happens in 3D printing as a means to dealing with this particular quality issue when you get to printing parts.
Thank you, Brenda. Actually, we're coming back to you. A lot of people know how involved you are with ASTM, so there are some questions there already for you. But specifically, I'd like you to explain a bit, what does the product qualification process typically look like? And if you can explain some of the keys to success when trying to develop this product qualification.
Sure, absolutely. So the product qualification process is a lengthy and rigorous process that's used to demonstrate that a manufacturing process is capable and competent at producing a specific product. Often when people think of product qualification, they automatically focus on the testing of the manufactured product itself. But it's important to know that it actually involves a lot more than just the manufactured product. Product qualification starts at the facility level. This is the foundation of the manufacturing process. So is the facility capable of supporting the selected additive manufacturing machines and processes? Are there procedures in place to control the facility to ensure that it will always meet the needs of the manufacturing process? Once the facility has been controlled and qualified, the next step is to qualify the machine. Is the machine calibrated appropriately and adequately? Is a preventative maintenance procedure in place to ensure that the machine will perform as expected? Are operators properly trained to run the machine? All of these aspects of the machine must be documented and established prior to other qualification activities. So once the facility and equipment qualifications are complete, the next step is to qualify the material. Now we need to demonstrate that the material selected will meet the customer's requirements. How is the feedstock handled and stored? What material properties can be achieved with the selected material? Does that meet customer requirements? This portion of the product qualification process is significant and can take a lot of resources to complete, but it's also a critical component to being successful overall in qualifying an additive manufactured component. So once that material has been qualified, the next step is to qualify the process. What controls are in place to ensure that the process is repeatable and reliable? How is statistical process control being implemented to track and verify process performance? This effort really moves beyond just the material in the machine, and it really brings us closer to being able to qualify a specific part design. Once the process is qualified, we're finally ready to qualify a specific product. This is what people traditionally think of when they hear about qualification. This portion of the effort is where the manufacturer demonstrates that they can produce a customer product and that it meets requirements. This usually involves destructive testing to demonstrate that the actual product meets performance requirements. It may also mean other testing in relevant or operational environments. Once this is achieved, the product qualification process is considered largely complete. Of course, the work doesn't stop here, but it's definitely recognized as a major milestone and achievement. So then I'll answer the second part of that question as for some keys to success. I think there are a few to highlight. And really the first key is about culture. Achieving qualification is not easy, and it's something that's still new to the additive manufacturing industry. You really need to instill a culture of excitement in the team. You want your team to be excited by the idea of qualifying a customer product, excited and ready to do hard work. Without this cultural element, you may find yourself fighting an uphill battle with less than ideal support from your team. And the other key to success I'll mention is that of leaning on other quality resources. Most opportunities for qualification are not cut and dry. You'll find a lot of instances of ambiguity, and you'll need to rely on other sources to move forward on the qualification path. This might mean referencing traditional manufacturing quality standards and practices, and then modifying them to your process and situation. It may mean referencing standards and practices for other AM processes that aren't exactly like yours. Whatever situation you find yourself in, lean into it. Explore how others have done it and see how you can adjust it to make it work. The more we all succeed in this product qualification path, the better it will all get for all of us. And as I mentioned before, this all feeds into customer confidence and trust. Thank you, Addie.
Thank you. Thank you for that very detailed level of contribution. Humna, I'm wondering, how does metal AM standardization and quality requirements, I'm wondering how it differs across the industry.
The quality requirements, how they differ.
Yeah.
So, understanding from what I'm learning about some of the methods that I'm seeing that things are very, like defects and shift issues, things that may or whatever it is. What in object is not to take that was originally tested or process and then turn it additive. It's to design parts for additive. So we take a rocket nozzle and or an engine piece, and instead of the components being various components that are connected on the propulsional results that are needed, those are built into the walls, for example, of the part. So it's a whole new different design theory to be able to part, because they're not we've learned that it's not as successful to take something that's working and it's okay, better than just creating it from scratch, and metal additive as a resource for that. So I think in that sense, it differs greatly. One is in how complex you can design parts to remove all of the additional components and processes that would normally take for a part. We've designed an engine that was normally 64 parts in 2 parts, for example. Build all of the heating, cooling chambers out inside, and also how components and wiring is. So for metal, in my experience, is designing for additive is key. And I do say right now, at the point that it is in its maturity level, it is more costly. It's fast when you come to production. It does take longer to do. In the long run, it's lead us to reusable, cost efficient, and a lot more efficient technology, in the other terms.
Thank you. Now, I wanted to echo the fact that I have seen, especially on the application side, when customers just throw a part at you and say, "Hey, make me that part," and that part was probably casted in the past, and they expect you to build that block for them. And when you look at maybe if you ask for the question, maybe you ask for the finite element analysis result of that part, then you realize these areas are redundant. I could cut this place out and save 20% in terms of material usage and probably improve performance. But this conversation has to continue to happen, especially as traditional manufacturing companies adopt additive. It is our responsibility to educate and to do a bit more digging. Don't just take the part and try to manufacture, ask more questions, talk to the design team, look at their criteria, and help them figure out how can we optimize the part and probably improve functionality and show it to them, so we don't just try to manufacture parts that pretty much we're just making redundant parts. So in some cases, these parts can't even be manufactured well with additive, except if we modify. So thank you so much for sharing that. All right.
Absolutely.
So,
and just to add on to that, one of the things that I've learned is that you have to think when you're designing, especially again, only from my background is in aerospace and spacecrafts. When you're designing for something, you have to to its limit, tighter tolerances, you could achieve that you could not do. So that's another great purpose for metal additive, is to push the limit and push the envelope and be able to develop parts and vehicles that are far more advanced than what we've.
Great, thank you. Laura, for polymer, we're wondering if you could share a bit more about the typical metrics that are reported on data sheets to help designers select the right material for the application, and how do we characterize this quality and performance of polymer materials. I think that the first part really was to build on what Humna started. So we can, if there's anything you want to share in that, and then the second part is how to characterize this quality and performance.
Thanks, Addie. Data sheets are a topic that is near and dear to my heart because that's what my team does for our company. We create all the data sheets for our polymeric materials. And over the past few years, we've put a lot of effort into adding information to those data sheets so that our customers can choose the right material for their application, which is really key to meeting quality requirements. Material needs to perform in a way that's going to work in the application. So I guess what I'd like to do is walk you through a data sheet so you can see the kind of things that we're measuring, and that'll give you an idea of some of the metrics that we're reporting and how we do those measurements. So I'm going to share our ProBlack 10 data sheet. That is our most popular figure 4 material. Let me see. Why is that not showing up? Sorry, let me close some stuff. I don't know, Addie, I'm not seeing my, oh, here it is. Wait, I got it. All right, there we go. Can you see that? Okay, I think I can see that it's working. All right, so this is just going to walk through the data sheet here. And of course, this first page is just mostly a marketing summary. But one thing I just wanted to point out here is that it is noted that all the properties are based on using the documented post-processing method, and any deviation from this method could yield a different result. So one of the challenges even with making data sheets is that they're very specific to the process that is used to create the data. And so we try to be very specific about how we created the data sheet so that if someone wants to reproduce it, they would have instructions to do that. So the first section of our data sheet is just a whole bunch of material properties. And this is pretty similar to what we've done for a long time. We show a wide variety of metrics that engineers might need to understand in order to choose the right material for their job. We publish both ASTM and ISO standards because, in different industries, different standards are more important. And then as we create the numbers that go in here, we typically test 3 sets of samples for each metric. That might be 3 different lots of material or printing on different printers. And we do our best to follow the standards. For example, our lab is climate controlled, so we maintain a 22 degrees C and 50% humidity environment. We also make sure that the specimens meet the ASTM standards regarding their geometry and surface finish. And sometimes that does require some additional finishing in order to meet those standards. Fortunately, with the photopolymer technologies, it's relatively easy to meet the requirements, but you can imagine it can be much harder with the lower resolution technologies to meet those standards. And we are well aware that the standards were not written for AM materials, so my team is also very involved in ASTM and on some of the committees working to make those standards more inclusive of AM materials. And there was a question about density, I think, in the chat, and we use ASTM D792 if you want to check that out for the way that we measure solid density of resins, which is what this is a liquid material. So once you kind of have an overview of the different mechanical, thermal, and electrical properties of the material. The next thing we like to cover is the isotropic properties. So that would be when you print in different orientations, how does that change the properties of the material? The VAT photopolymer technologies are pretty insensitive to orientation, but there can be huge differences in some of the other technologies like FDM, whether you're printing with the layers or against the layers. So this is in the case of figure 4, we just do 4 different orientations, which are shown in these pictures. And this is a case where we do have to do extra finishing. Our default orientation for printing is in the Z-axis, and that puts the supports on the end of the sample, which means we don't have to do anything special in order to test those. But when you have samples on their side or at an angle, you're going to have supports in this area, and we do finish those areas so that there's no witness marks for the testing. The next section of our data sheets contains information about long-term stability. And that is measured using QUV testing, so UV and weathering testing. And it really is acknowledging that we're trying to increase adoption in end-use applications. And so designers need to know how the materials might behave in a real environment. So the indoor stability test is just UV and temperature, so constant UV exposure. And this test is a pretty well-established acceleration factor, so that about 600 hours is equivalent to 8 years in real life. And that would be indoors with light coming through a window. And you can see this material is quite stable under these conditions. We've got the strength, modulus, elongation, and impact strength here. They're all pretty flat across the whole 8-year span. So this material probably is a pretty good candidate if you're doing an indoor application. The outdoor test is a lot harder. As you might imagine, this test actually cycles between like a sunny, hot day and then a cool and dewy evening. So there's moisture involved in the test, and it's cycling between light and dark. In this case, we've done our own work to develop the acceleration factor, and 600 hours is only about 1 year of real exposure. And you can see for this material, several of the metrics are stable, but we do see some degradation in the elongation, which tends to be the most sensitive metric, and which would indicate, depending on how long you're going to use this in some sort of outdoor environment, you may see some degradation. And then the last section I'll go over is our fluid compatibility testing. And that is, we actually do 2 sets of fluids. We do the automotive fluids, which is what I have shown here. That's based on the US car standard. And then we also do some other fluids like solvents and water-based systems like liquids and bases, which is an ASTM standard. But the basic concept is you expose the printed object to this liquid, and then you measure its properties at different times to see how they might have changed with the exposure. And that would help you if you know you're doing an application. So for example, if you're doing an application with gasoline, this material is pretty stable in gasoline. However, if you're using engine coolant, it looks like it's going to absorb a lot of that material and become plasticized. So it might not be a good application for this. So this can also help a designer choose the right material for the environment the material is going to be in. And I'll just real quick scroll through the fluids we do for the ASTM chemical compatibility, which is pretty similar. And then the final sections here are biocompatibility, which we send out to a third party, actually. And then finally, we have the post-processing instructions, which you could follow if you wanted to actually reproduce data yourself for this, this type of thing. So this is an example of the kind of data we provide our customers, and choosing the right material for the application is super important in quality, because you're not going to have quality if you don't have those basic parameters figured out. I know we're getting close to the end of the session. If you'd like to chat afterwards, I'll be on the 4th floor at the 3D Systems table. But for now, I'll send it back to Addie.
Thank you, Laura. That was really good. Thank you so much for taking time to share that. And we want to quickly go to Brenda. You've talked to us about what your customers are talking about when it comes to quality issues, what they're seeing. We know you're talking to 3D printer manufacturers as well. Can you share with us some of the things that different 3D printer manufacturers are telling you as to how they are addressing these issues that are coming from their customers, and some of the things we may see in the future 3D printers that we will purchase.
Yeah, I'll stick with the topic of vibration. So the 3D printer manufacturers they have dedicated engineering teams, and they've tried a lot of tried to solve this vibration method problem with a lot of mechanical means. But at this point, it's diminishing returns. And so they're turning to software. One of the specific approaches that they're trying to implement is input shaping. In fact, some of the manufacturers we're talking to are considering moving to Clipper as the firmware because of the input shaping feature that it includes. There are a couple of challenges with that, though, they're sharing with us. Number one, you have to add some hardware. So that's additional cost to the bill of materials, to the build of the printer. The other issue is because of the nature of the input shaping vibration compensation approach, it introduces quality issues of its own. One example is rounded corners. So some of them have told us they've tried to implement input shaping, and then they kind of turned off the feature because their end customers are saying, boy, it introduces these other things, so we're not really interested in it. You may have heard that in the latest release of Marlin, the Marlin team has introduced a very light, I would call it light, and they would agree with it, light input shaping approach. I'm happy to share that Ulendo has decided as a company to contribute our input shaping methodology to the Marlin open source project. And that should be coming out later this year, hopefully before the summer. The great part about that is that it doesn't require any additional hardware to be added to the machine. So it's a much more cost-effective approach for the 3D printer manufacturers. And if for some reason, and if they're still not satisfied with what you can get out of input shaping, even ours, they could upgrade to Ulendo's FBS product, which is based on filtered B-splines. So we're looking forward to seeing continued advances in compensating for vibration, which is one of the things that are driving quality issues in a subset of 3D printing.
Thank you. Before we close, there's this one question. We don't have a lot of time. And I want to take this one question for Umna. Can you describe fatigue, cyclic, dynamic testing done for customer products? And if there are any standards that are made? I know this is not a 1-minute question, but if you can give us a summary, that would be great.
Yeah, so there's the low cycle fatigue, the high cycle fatigues. There's standards made for it. We have ASTM E466, E606 for just two simple high cycle and low cycle, and we usually do some tensile testing right before to get the stress and plot fatigue curves in order to be able to achieve a certain strength. This depends on like cyclical values, R ratios, and heritages that we try to develop with your material. So especially if there's a material that doesn't have much data out there, it does take a few different like what we would call a fatigue qualification test. Could be anywhere from 50 to 400 bars of determining in on what would be the fatigue expectation. There is like the MMPDS, which is a great source for understanding metals, but we see in the additive realm that there's so many other things that influence it based on post-process or heat treatment. So it really helps to determine what the longer lasting cyclical failure expectation is. If you want, you can message me, but it's really a passion to understand material and what's the limits that you could push on. You could actually expect the environment you're in. So we have heat treated fatigue. I mean, in elevated temperatures, cryo with certain surface roughnesses, ones that have coatings on polishing. So it's a whole other the application is, to point you in the direction to the correct spec. So develop a qualification standard for your own personal material and for whatever you're printing.
Thank you so much, Amna. There's so much questions. People have questions for Andrea, for Brenda, for Laura. So I would say, everyone, we have passed that time at 2 minutes. So we'd like to stop so that you can go and network. One thing I know for sure is quality is very critical to sustaining additive as a technology that will stand the test of time. So as we all think about what we're contributing in this industry, let's remember that people are critiquing us. People in traditional manufacturing are asking questions because of the fact that they want to adopt this technology. Let's ensure to keep quality first place. Some people here need to join ASTM standards to help us with writing standards. Some people need to join ASM, other places. Some people need to help us work on, quality. We have so many different industries right now looking at not just laser powder fusion. They're looking at binder jetting. They're looking at other places. Please, let's work together to ensure that we are prioritizing quality so that additive can be here 20, 30 years. And we can see it in different engines, in different places, in our shoes, as a technology that will really stand the test of time. Thank you all for your contribution today. I feel so proud that I brought together these powerhouses to lead this conversation. It's beautiful. Thank you all for your time. Thank you all for sharing your knowledge. Please connect with the speakers on LinkedIn and further ask them questions as they stay in different places today. Thank you all, and we'll go on a little break and come back later. Have a wonderful day, everybody.
Thanks, Addie.
Thank you.
Thank you.